GridSearchCV is the #1 way people waste days. Here's the drop-in replacement that gets you better params in minutes. This is the workflow you'll know how to run when we're done, which samples hyperparameters efficiently with leak-safe folds and then locks reliable settings. I'm Professor Pi, teaching AI foundations with simple Python. Hyperparameters search is where model quality and developer patience meet. People reach for exhaustive grid search because it feels thorough, but it scales poorly as you add parameters. Randomized Search CV gives you better odds in far less time. It samples combinations intelligently, uses cross-validation to avoid optimistic scores, and gets you to a reliable setting you can trust on new data. Success looks like higher holdout performance with a fraction of the compute and the same safety against data leakage. At an intuitive level, imagine throwing darts at a wide target instead of measuring every millimeter. Randomized Search CV spreads its samples across the space. It finds regions that work well, and you can zoom in later. The trade-off is simple. Randomness risks missing a tiny sweet spot, but with clever sampling and more iterations, you cover far more useful ground than a tiny grid. We will build a tiny project that proves the point. First, we create a reproducible baseline on a clean train test split. Then, we wrap pre-processing and model in a leakage-safe pipeline and measure cross-validated performance. After that, we launch Randomized Search CV to probe hyperparameters quickly, widen the search to show how many configurations were tried, and finally refit the best pipeline and evaluate on untouched test data. It stays simple and shows the full search to deployment loop before you scale it up. Now, we'll establish a baseline to compare against. This snippet quickly establishes a baseline classifier and evaluates it on a clean holdout set. It creates a toy binary dataset with make classification, fixing random state to make results reproducible. The train test split call preserves class balance via Stratify and uses a fixed seed so the split stays the same. A LogisticRegression model is instantiated with a higher max iter to ensure convergence and then trained on the training portion. The model's predict-proba method yields class 1 probabilities, which feed into ROC AUC score for threshold-free evaluation. Increasing test size lowers variance in AUC, but reduces training data. The printed holdout AUC is your starting quality before any tuning. Next, we'll make cross-validated evaluation safe from leakage. This example builds a scikit-learn pipeline that standardizes features inside cross-validation to prevent data leakage. The pipeline first applies StandardScaler and then trains a logistic regression using the liblinear solver, which supports both strong regularization and small datasets. A StratifiedKFold object sets up balanced folds, ensuring each split preserves the original class ratio. The cross-val score function evaluates the entire pipeline end-to-end, refitting the scaler and model within each fold, and returns ROC AUCs across folds. Raising end splits can reduce variance, but increases computation. The printed CV AUC summarizes leakage-safe, cross-validated performance and gives a more reliable baseline than a single split. Now we'll launch a quick randomized search to probe useful hyperparameters. This snippet launches scikit-learn Randomized Search CV to quickly probe the hyperparameter space for the pipeline. The dictionary params targets pipeline fields using their step names, exploring C values and penalty types for the logistic regression named CLF. Randomized Search CV samples n-iter combinations at random, evaluates each with the provided StratifiedKFold, and scores them using ROC AUC. Setting random state makes the sampled combinations reproducible. and refit equals false avoids retraining the final model yet. Increasing n-iter broadens the search and often finds better settings at the cost of time. Decreasing it speeds up runs but may miss winners. The printed best _CV AUC reflects the strongest cross-validated score discovered. Next, we'll widen the search space and count how many sets were tried. This snippet widens the search space and shows how many configurations Randomized Search CV actually evaluated. The params2 grid adds more C values, spacing them across orders of magnitude to capture both strong and weak regularization. Randomized Search CV samples 30 random combinations from this space using the same cross-validation and scoring strategy as before. After fitting, CV results contains per-candidate metrics and metadata. Counting its params entries reveals the breadth of the run. Increasing n-iter improves coverage and the odds of finding better hyperparameters, but increases runtime. Fewer iterations do the opposite. The printed tried configs confirms the number of unique parameter sets tested in this sweep. Finally, we'll refit the best pipeline and evaluate on the untouched test set. This example finalizes the model by refitting the best pipeline on the training split and then evaluating on untouched test data. Randomized Search CV runs the same search as before, but with refit true, which automatically trains the best estimator on all of XTR and YTR after cross-validation. The predict proba call on XTE yields probabilities that feed into ROC AUC score for a clean, threshold-free metric. Using the held-out test split ensures there is no information leakage from the search phase into evaluation. If you increase NITER here, you may squeeze out a bit more accuracy at extra cost. The printed test, AUC, is your production-ready, unbiased score. Mapping to a real project, this pattern moves straight into model selection for real datasets. Replace the toy dataset with your feature matrix and labels. Keep the pipeline steps that reflect your pre-processing needs, and run the same randomized search. The holdout test remains your final check before deploying a model to users. Recap: it is Randomized Search CV in scikit-learn that samples hyperparameter combinations randomly across a defined space. Use it when grid search is too slow or the search space is big and you want better coverage for a given compute budget. Caveat: randomness can miss narrow optimal pockets, so validate with a held-out test and consider increasing iterations if results vary. Wrap punch. Next, try increasing the number of random samples beyond the 30 used in the wider sweep and measure the runtime versus holdout AUC to find the sweet spot for your workload. If AI Foundations in Python help, subscribe and watch the AI Foundations videos.